Popularity of AI has been exploded since ChatGPT came out. Then other tools like Claude, Gemini, and thousand other followed the trend where people are talking about these all day. Whereas technical folks are flexing by telling everyone core stuffs like parameters, the way it trained RLHF, the amount of GPU memory it takes, how it can take over the world, make you jobless, destroy humanity, blah 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 blah. Although these are the things which are not completely wrong, and it's good that people are talking about it, but one thing which almost no one or very few people talking about is a single tool that makes training large language model possible. And it's a core thing which I think if not everyone that at least technical folks should know. I'm talking about a training mechanism which can scale up to train billions or even trillions parameter of model and is backbone of training modern LLMs. In this video, we'll see how fully sharded data parallel, or FSDP for short, works and how it became the most important contributor to modern AI sensation. The word sharding means division and distribution of data or model parameters into manageable pieces. We call these pieces shards. In our case, sharding means splitting a model into chunks and sending them across multiple GPUs. Traditional methods of data parallelism, where each GPU holds a full copy of model, gradients, and optimizer states, have become increasingly impractical for these large models. FSDP addresses this challenge by allowing us to effectively distribute not just the computation but also the model itself across multiple devices. This enables the training of models that would otherwise be impossible to train due to memory constraint. While training a deep learning model, these are the three essential things that consume most of the memories, and those are the model parameters, gradients, and optimizer state. Let's see an example to get this clearly. Let's say you wanted to train a GPT-2 on its standard input context length, which is 1024 tokens, and let's see how much memory it is required to train this model. So we know the parameter size of GPT-2, which is 1.5 billion parameters. Input context length is 1024, and assuming batch size of 32 and precision of 32-bit floating point. First, memory required for model, which is number of parameters times size of precision, which is 32 bits or 4 bytes, will consume roughly 6 GB of GPU memory. Now same required for storing gradients as well, which is number of parameters times size of precision, it's also 6 GB. Third is the optimizer state. So if you're going to use Adam, which has 3 additional variables per parameter, and those are momentum, velocity, and parameter itself. So the memory required for it will be number of parameters times size of 32-bit precision times 3, which is roughly 18 gigabytes of memory. And now for calculating memory requirement for activations, we need these informations. We know that we are training on a batch size of 32, sequence length of 1024, and we already know that GPT-2 uses embedding dimension of 1600. It has 48 number of layers and 24 attention heads. So here are memory requirements for storing token embeddings. So the total memory for this will be the batch size multiplied by sequence length times embedding dimension times size of float 32, which is roughly 0.2 gigabytes of memory. And similarly, we can compute for positional embedding as well. It will be sequence length times embedding dimension times size of precision, which is roughly 0.006 gigabytes. For layer activation, for each layer we need to store self-attention outputs, which is 4 tensors, query, key value, and its output. And second one is feed-forward intermediate and its output. So first compute for self-attention, that we can use 4 times, since we are having 4 tensors, then 4 times batch size times sequence length times size of embeddings times size of precision, which will be computed around 0.78 gigabytes or roughly 0.8 gigabytes. And similarly, we can do for feed-forward as well, which is 2 times batch size times sequence length times size of embedding times size of precision, which is roughly 0.39 gigabytes. So the total per layer will be around 1.17 gigabytes. So this is for only one layers, and we know that GPT-2 1.5 billion parameter has 48 layers. So we just have to multiply it by 48 and we can get the memory requirement for all 48 layers will be 56.25 gigabytes, which is huge. Now it's time for compute for total activation memory. So that will be the sum of token embeddings, positional embeddings, layer activation, layer normalization. which will be roughly 56.43 gigabytes. And by summing them up, we'll get total GPU memory required to train this model. So which is parameters plus gradients plus optimizer state plus activation, which will require 87 gigabytes of memory. Despite that, I neglected temporary variables and other factors, so the minimum rough amount of memory you will need to train this kind of model will be this huge. Now consider if you take NVIDIA's A100 GPU, which has 80 GB of VRAM, you'll still end up disappointing by those extra 7 GBs. So how are we gonna train it? One solution to this problem is to shard the model layers to different GPUs. For example, if you have a model with 6 layers and you have 3 GPUs, then you can distribute 2 layers to each GPU. This method will solve the problem but not that efficient, because since the layers are distributed in such a way that require process to happen sequentially, like when GPU 1 will be computing for layer 1 and 2, the other 2 GPUs will sit idly doing nothing. So this is not a good way to shard the model. So what's the best way? Okay, imagine instead of sharding model layer wise, what if we shard the layer across multiple GPUs? So let's modify this example, and now we split the layer across all GPUs. For example, we can split parameter of layer 1 into 3 shards and distribute across all GPUs. Now since a layer is distributed across each GPU, all of them have to work together to compute output for that layer. And this method seems quite efficient. This is what happens in FSDP, which stands for Fully Sharded Data Parallel, and now you know the reason behind its name. Let's see how exactly it works. Believe me, it contains a lot of tricks. Let's take the example we used before and now assume that this layer has parameter of 1024. Now you have 3 GPUs. Let's shard the parameter across all of them and you'll get this. Every GPU must have 1/3 of the total parameter, and that's the initial step. Now if you send a data in a batch of 96 samples, the batch has to be divided into 3 parts as well. And hence each GPU will have 1/3 or exactly 32 samples. This was the first step. Now you are going to perform a forward pass for layer 1, and here comes the all gather operation. As the name itself seems self-explanatory, all gather operation is used to get shards from other GPUs to one place for computation of parameter on that batch. Let me explain this a bit. We have these 3 GPUs contains their respective shards and local batches. All operation for GPU 0 will require gathering shards from GPU 1 and GPU 2 to GPU 0. And similarly for GPU 1, it will gather shards from GPU 0 and GPU 2, and same happen for GPU 2 as well. Now since each GPU is having all the pieces of shards, they can reconstruct the full parameter of the layer 1 and compute a forward pass for their local batches. And this operation will happen parallelly, so no GPU will have to sit idly, and also no need for GPU to communicate with each other. This solves a problem of GPU sitting idle as well as reduce communication overhead. Please note that the local batches will not be shared during this operation. Once the operation is finished, full parameter will be immediately discarded to save memory. However, the original shards will be kept in the GPU for backward pass. And similarly, these operations will happen for all the layers. So this was the second component of FSDP. Now this is OG and little complex. So let's dive in. First, it will perform all gather operation to get the weight shard from all GPUs to each GPU. Similarly, what happened in forward pass. And then it compute gradient on their respective local batch. Now once the gradient computation is completed locally on each GPU, the weight will be updated for their respective batch on each individual GPU. And here's the tricky part, and think about it. We know that each GPU got weights from other GPU, hence it computed gradients, so we can say that each GPU has information about gradients of other shards as well. And hence, same goes for updated weights as well. But we want to store updated weights of respective shards in each GPU and discard other shards to save memory on each GPU. And here's the tricky part. We know the indexes of weights stored in a GPU because of how it was distributed initially. So we can slice those ranges of indexes from the weights to get the particular shard and discard every other. And now we have updated weight which contains info about local batches in other GPUs as well. This step is called reduce scatter, which is used to share the aggregated gradient shard to each GPU. And hence we are ready to feed a new batch. And here is a mathematical expression for you to remember this. Imagine this example input and weight. which will be splitted across 3 GPU, and their combined output will be equivalent to this, which is full batch times full weight. Remember that all gather and reduce scatter belongs to NVIDIA Collective Communication Library, or NCCL for short, which is made for distributed computing like this and gave crucial contribution in FSDP. And here we are, end of this video. FSDP is quite tricky. I found myself struggling with a lot of things while trying to understand this, and hence I tried to cover everything from A to Z in this video and got this far long so that you don't have to struggle. So if you are with me so far, thank you so much for watching and your support. And as always, here are 3 things that you need to remember from this video. FSDP made training LLMs possible using distributed computing by sharding the model parameters across each node. Unlike distributed data parallel or DDP, it reduces memory footprint and communication overhead. NCCL plays a crucial role for performing operations like all gather and reduce scatter, which made this algorithm work seamlessly. I'm also planning to write a blog on this, so please stay tuned. I will update the link in the description once it's published. Thank you so much for watching, and I will see you in the next video, and very soon, I promise.